Welcome back to our video lectures for system dynamics and vibrations. Today we're going to start talking about second order second order differential equations and second order systems. So a bit of a review maybe from dynamics. If you're looking at a block that's sliding without friction on on a surface. We'll move the wall a little closer. And there's a wall right here. Say this block has a mass m. Say it moves in the x direction and it's attached to the wall with a spring with stiffness k and a damper with a damping coefficient of b. Right? There's no forces attached to this thing. We can come up with a free body diagram where we have some force kx, some force b, x dot. That's going to equal the accelerations. And the equation of motion for this system is going to simplify to mx double dot plus bx dot plus kx equals 0. And so this is a linear second order constant coefficient ordinary differential equation. And not just this system, but a lot of systems can be simplified to look something like this. You can imagine if it was a rotational system, then the x's might be thetas, but the equation is going to look more or less the same. And so this equation is specific the uh, to the system that I just drew. The mass is the m for the mass is specific to the system. Same with the damping coefficient and the spring constant. And so we want to be able to write this in a way that is more generalizable. And so we're going to have what's called a general form of these linear constant coefficient second order differential equations. And we're going to write it like this, where it's x double dot plus 2 zeta omega n plus, sorry, excuse me, got ahead of myself, 2 zeta omega n x dot plus omega n squared x equals 0. And so any equation, any second order system, any linear constant coefficient second order system can be rewritten in this way. And we're going to, this is going to be the general form. And these variables have special names. So zeta, which I write like that, that's not my best zeta. I'll rewrite it again so you can recognize it later. Has a little bit of a loop and then a bump down there. That's what's called the damping coefficient. So similar to B was our damping constant for the physical system. This is a damping coefficient. And omega n is the natural frequency. And so you might notice um, that there's only two variables here instead of three with the mass, damping constant, and spring constant. Um, but with these, we can describe the system. Um, and so to convert between them, you notice that the coefficient in front of the x double dot is just, there is no coefficient, it's just 1. And so to come back here, we can relate between um, this physical, the physical representation of the system and this analytical representation by um, dividing the mass out of the physical representation. So if we divide this entire equation right here by m, come back to the bottom, we get x double dot plus b over m, x dot plus k over m x equals 0. And then we can relate these things. So 2 zeta omega n is equal to b over m. That's just because the coefficients are all the same. And omega n squared equals k over m. And so with that, we can say, with that second equation, we can say that omega n is equal to the square root of k over m, and zeta, with a little bit more algebra, is equal to b over 2 times the square root of m times k. And so these relationships help us convert between these two different representations, two different ways of looking at the system. And so omega n and zeta, these are ways of talking about different systems that may have completely different masses, completely different stiffnesses, but if two systems have a similar zeta and a similar omega n, then they're going to behave the same. Um, and we'll talk about zeta real quick. So if zeta is less than 1, we call that an underdamped system. And we'll talk about this more in future lectures, but want to get this out there right now. If zeta equals 1, that is a critically damped system, and if zeta is greater than 1, that is an overdamped system. If zeta, I'll put this up here, equals 0, then that's an undamped system. There's no friction, no dissipation in that system. So we'll go ahead and take a break, and we will pick this up in the next video.